Hello everyone, Andreas here. Today we talk about 750 kilovolt case. In the beginning I'll start a little bit about Ukrainian 750 kilovolt grid, show our how our substation look like, and then we dive deeply in case study. So we took at the primary scheme, then look at Soviet protection philosophy, then analyze event, and in the end I talk a bit about modern designs and modern philosophy. So the topic is very complex for me, so please type your questions. I'll be happy to answer to them. So you can Google in Google search type INSOI grid map, and there is a map of the Europe countries grid, and this is Ukraine in the 750 kilovolt line shown in this dark blue color. So this dashed line is for plant lines. Now it on the design stage. As you can see, this voltage level is really like grid forming level. This river Dnieper and this territory now occupied. So, but I don't want to show like on substations on territory that are controlled by Ukraine. But this substation was one of the newest. This line was commissioned in just before the war. So let's look at Google Maps. So this is that substation. So this is one bus bar, another bus bar line. This here circuit breaker, shunt reactors, and here neutral reactor and corresponding circuit breaker. This is group of the single phase, two groups of the single phase transformers with phase shifting transformers. Each phase rated power is about 330 MVA, and overall rated power of the overall group is about 1000 MVA. This line connected through two circuit breakers. This area is for second circuit. It's shown here by dashed line. Here the 330 kilovolt switch yard. So this is the web page of the company that built substation, and here we can see a little bit more detailed image. So this is a group of auto transformers. So circuit breakers and circuit breaker of the shunt reactor. So this line connect this substation with nuclear power plant in Zaporizhia. It's also now occupied by, I show you how it looks like. So this is 6 reactors, each has power about 1 gigawatt. This is a 750 kilovolt switch yard. All generators connected to this switch yard. This is the news circuit. You can also see shunt reactor, and neutral reactor. But these like old circuits, and here you can see only a shunt reactor. Also, only one group of auto transformers connects 750 kilovolt grid with 330 kilovolt, and here you can see 4 transformers. This is the spare one, and if this is usually used in all designs, and if we need to repair or make maintenance to one of these auto transformers, we can just use this one spare auto transformer. So let's move to our case. The primary scheme showed a little bit simplified. There is no disconnectors, SN switches, surge arresters, but it will look very messy. Just here it almost very complex. So I want to start with CT transformers. There are 3 CT transformers: line transformer, CT, and each circuit breaker has its own CT. Usually it can be 2 breaker per line, or maybe breaker and a half scheme. These current transformers are built in bushing of the shunt reactor, and in this particular case we have only shunt reactor and not neutral reactor. There are 4 voltage transformers, and each protection can be switched to any of these voltage transformers. So shunt reactor have 2 branches, and it has 2 different differential protection, and modern designs for longer lines usually have this neutral reactor that usually is shunted by this low voltage circuit breaker. Usually its rated voltage is 35 kilovolt. Usually the power of the single phase of the shunt reactor is about 110 MVA, and this reactor is around 16 MVA. So let's talk a little bit about protections. So this case is from 2016, and the whole protections were from Soviet era, and in Soviet Union, the most advanced protections was from series that called PD 2000, and it has various protections. So for distance protection was 2001, and it has only distance protection for multi-phase short circuits. 2002 protection is directional neutral overcurrent protection with instantaneous overcurrent. 2003 is we call it directional phase directional differential protections. I talk about it a little bit later. And 2004 is for automatic reclosing. It has phase selectors, and it can do single phase strips and are three-phase strips with various controls. 2004 used for breaker failure protection, and 2006 is busbar protection. So usually line equipped with various high-frequency communication channels. The main protection uses one, and there are also transmitters and receivers that can transmit around 16 signals. We usually call these signals commands, and in this particular case it was used four signals for protection, protection, and in one from a substation A to substation B transmitted 7 system integrity signals, system integrity protection signals, and from substation B to substation A transmitted 10 system integrity signals. So, in Ukraine, system integrity protection is the whole universe, and it's signals transmitted not just about between two substations, but it can came from one part of the country and went to another part of the country, and there trip 200 megawatt of load. And there are a very complex interaction between all of these protections, and these transmitters and receivers. We'll also talk a little bit later. So this is like look. They look. I can say that this protection is very rare, but it's difficult to find good photos of them. So let's start with distance protection. As I said earlier, distance protection from PDA 2001 is only for multi-phase short circuits, and it has characteristics that look like that. PDA 2002 has 4 directional steps for neutral overcurrent protection, and as I said earlier, instantaneous overcurrent protection. And okay, let's talk a little bit more about the main protection that called PDA 2003. So I don't see the any modern or Western protection like that, and because it's not only phase differential protection, but it combined. So it has two. I believe you know about distance blocking schemes, but here used the same principle, but not with distance relay, but with negative sequence directional power relay. So protection has two of the relays. One works for blocking direction, and while during external short circuits, and one of the protection is one of the relay is work in tripping, when power. When short circuit is on the protected line, and this vector diagram shows the vector diagram of the voltage, negative voltage, negative sequence voltage, and negative sequence current that shown vector diagram for short circuit on the protected object. And this vector diagram shows the case with external short circuit. And the main feature of this protection that it trips and usually trips through this 2004 panel that has its own phase selectors, and it trips single phase, and during single phase R cycle, this PDA 2003 switches in phase differential protection. And after end of the cycle, it switches in normal condition. So if talk about a little bit about phase differential protection, so during the short circuit on the protected object in a high frequency channel, we will see such picture with pauses, and protection trips in this pause. In case of the external short circuit, there is no pauses, and protection not trips. Also, this protection has distance relay in case of switching of the solid three-phase short circuit, because it needs any negative sequence to start, or in for tripping or blocking. So in case of solid three-phase short circuit, there are no any negative sequence, so this protection can fail in this case. What I want to say that on a line CT is usually connected auto-step protection measurement. I showed here digital fault recorded, but usually it connected to all of the CTs. So the shunt reactor has insulation monitoring system for bushings, and also Buchholz relay. And now I want to talk about R's, because it's very complex. So usually single phase R start this 2003 directional differential protection, first step of the distance protection, first step of the neutral overcurrent protection, and also instantaneous overcurrent protection. And usually in this 2003 panel, the third step is like very complex, and it used for SOTF functions. Also it used to control and send signals through these high frequency communication channels. And usually I believe and it used for like teleprotection permissive scheme, and this third stage is used to start a single phase R. If talk about three-phase R, so usually it starts not start by any protection, but it starts with difference between position of the switch that commands to open or close circuit breaker and position of the circuit breaker. And we need to say about that stages or zones that work with our inhibition, and so usually second and third zones of distance protections trip three phases with our exhibition and sending to the opposite end command for a three-phase tripping. Also, second, third, fourth steps of the directional overcurrent protection with its own times also trips, make three-phase trips with our inhibition and sending command to the opposite end to trip the opposite end. So if talk a little bit more about this protection commands, so as I said in the beginning, for protection needs used four signals. First signal is tripping without any controls with our inhibition. The second command is used for three-phase tripping with control from on opposite end, and control is from second zone of distant protection or third zone of neutral overcurrent protection. And usually the tenth signal used also by is by like a teleprotection. It's sent when single phase R is start, and on the opposite end this signal also controlled by third stage of the neutral overcurrent protection, and all the last protection command is 16 command, and we have numbers that everybody in Ukraine know what number means. So the 16 command signal is used before any trip for teleprotection with third stage of the directional neutral overcurrent protection. So I want to add that this first signal that used to trip the opposite end with our inhibition is also sent by breaker failure protection, and this shunt reactor breaker failure protection Auto-step protection sends this signal, this over-voltage protection sends this signal, and the last on this neutral overcurrent protection, the fourth stage, usually used in combination with pole discrepancy protection of the circuit breaker. So if we have problems with any phases on circuit breaker and there is zero sequence current, so fourth stage usually trips, make three-phase trips with first signal sending to the opposite end. I believe I say all about signals are, and before we dive in our case, I would want to add a little more words about single phase R by itself. As you will see in such high level voltage, the three-phase trip is more stressful to the equipment than single phase, and single phase during three-phase trips also can be swings in the grid, so like any big system events. So for a lot of reasons, it's better to just trip one phase. And the main problem with single phase is that during this pause, the arc can be difficult to went away, because the healthy phases that in work through the mutual coupling and also mutual capacitance like give life to this arc, and so the main problem is to determine the time of the life of this arc. And a lot of things are made in such voltage level to decrease this time, because theoretically it can be 1-2 seconds, but on practice, and we will see it, not usually very long. Okay, let's move to our case. This is the substation A side. Through the voltage we can see that and current that we have had single phase short circuit on the phase B. Also we can see that one of our breaker was in service, in maintenance, so in this primary scheme we also we can see this is current from shunt reactor, and we can see zero sequence current before the event, and that phase C also has like noise, and this also means that during this event one of the phase of the reactor, phase C, was in maintenance, so we don't have this phase. So let's look. Let me switch on my camera. So from the substation B side, picture is pretty much the same, but I want to show this high frequency signals from main protection. So this is signal from adjacent line, and this like blocking signal. So and this signal is from protection that protected this line with a short circuit, and in the beginning we can see some spikes, but here is a digital signal that shows that in that time we already had a trip. Trip signal asserts, and I want to show overall tripping time. From that side is about 61 milliseconds, and I believe here it's a little bit faster. Yes, 52 milliseconds. And this current shows the pause of the single phase R. So it was around 1 second, and from substation A side the circuit breaker closes first, and because it was solid fault, it trips again and sends this first signal to the opposite end for three-phase trip. And if we look to the opposite side, we have this we don't see any of current and only three-phase trip. And I want to say about over voltages, because as I mentioned earlier, from substation A side we don't have one of the phase of the shunt reactor, so on the substation B side we can see that voltage on the phase B is yes, this point. So usually phase voltage is around rated voltage 433 kilovolt, but during this switching on the phase C, over voltage phase voltage was in that point 525 kilovolt. So and this is like one of the main problems of the such lines, and one of the I believe that one of the main protections is this over voltage protection, and I forget to add some words about it. It usually has two stages, and first stage is when voltage is like 15% higher than rated voltage, and with zero time it usually closes this circuit breaker if before event line worked without a shunt reactor. And after I believe 7 seconds it trips all line with sending to the opposite end tripping signal. The second stage is usually set to 30% over voltage, and it trips a line during 250 milliseconds. And with over voltages, one of the problem is that it can be very high during period of time while a line is connected to the grid only from one side. And this because not only because of Ferranti effect, but also it can be happen because of the after like half of the second the line can start generate a second harmonic, and this can be the problem because operational staff don't see this second harmonic, and because all measurement devices are tuned to the first harmonic. So because of that, on a line usually implemented semi-automatic energizing and de-energizing, and I want to show like an energizing process. So and how did it happen? So usually done through the automatic reclosing. So operational stuff enables from the one like let's say usually before energizing, operational staff determine from which side to put the voltage on the line. So like on the opposite end, operational staff enables this semi-automatic scheme, and when voltage is line is energized from substation S side during 30 milliseconds from the substation B side, it will be switched like through the with all controls from substation B side through the R scheme, and this records is showing this process. So I make phase A voltage as base channel, add it to vector diagram, and we'll see the phase A line and reactor. So now the voltage is from substation A side, and we can see this capacitance current, and so let's measure the time. I believe it must be 30 milliseconds. Oh, it's less. 150 milliseconds. And here the line was in transit. So, but we can see that current in reactor is have inductance character. So I want to show this record because so you can see how quickly it happened in life, and if we need to de-energize a line from at substation A side, operational staff enables sending a first signal through the high frequency communication channels, and while it opens circuit breakers, also first signal is sent to the opposite end, and it automatically trips these two circuit breakers. So let's return to our case, and I want to prove that main protection worked correctly. So I'll calculate negative sequence current and voltage. Let's start with voltage. And then current. Let's make voltage as base channel. So maybe there is some mistake. There is something incorrect. Maybe I calculated zero sequence current. Sorry. Let's do it again from scratch. So sorry, I just don't hurry up. Line. Так, A, B, C. And negative sequence channel. Okay. Negative sequence channel to voltage UA, UB, UC. Okay, so I show you all this one to move. Okay, so now I calculated all parameters correctly, and we can see the picture that I shown you in the beginning. So during short circuit on the line, the negative sequence power is directed from line to the substation, and it has like this vector diagram. So the directional negative sequence power relay is worked to trip. And I also can show from the substation B side. So let's calculate parameters from that side. Let's start with voltage. UA, UB, UC, and then with negative sequence current EA, EB, EC. So let's make voltage as base channel and add, so we see the same picture. So from the side of substation B, protection also see that short circuit on the protected object, and it trips from the both sides. And in discrete, in digital signals, this is like start of this protection, and this is signal is trip. And after trip, as I said in the beginning, it switches to the phase differential mode. And you can see this poses like on that picture. And if we look from substation A side, so here after switching on phase switched on fold, we can see that this pose a little bit bigger, and here we must see yes, this digital signal is trip signal from PDA 2003 protection system. So let's dive a little bit in determination of the how time of this arc life. It's not a simple question, and we need the voltage channel. Here it is. Let's make it a little bit deeper, a little bit bigger. So there are a few mechanisms based on which we can determine that arc went out, and one of it is that during life of this arc life, the voltage on the tripped phase has a very big amount of the high frequency harmonics, and as we can see here on the left side, we can see second, third, fifth harmonics, and you can see that after tripping it has just enormous amounts. And here it starts to decrease to the just not usual levels, but it decreased a lot because here in the start of the process is like second harmonic is 153% of the first harmonic, and here it's like 3 or 1%, and also we can see that voltage on this tripped phase is started to decreasing. So this signs of that arc is went out, and we can close the phase, but it depends, and because of the shunt reactors, and this time is very slow, and also this line not very long at all, and it's just a little bit more than 300 kilometers. So what another methods to determine that arc is went out? So we need to look at the phase relations between zero sequence current, zero sequence voltage, and voltage on the tripped phase. So this digital recorder is tuned to show minus zero sequence current. So first I calculate just usual zero sequence current of the line. Okay, here it is. I make it all smaller, make it a base channel, and add to the second vector diagram. Also I adding voltage on the folded face and zero sequence voltage. So, base, I want that to be base, and also okay. So let's see. This relationship is during the fold, but when one face is stripped and arc is alive, so this angle between zero sequence current and voltage on the stripped face will be around 90 degrees, and after it changes and the difference between these vectors became very little, it also means that arc is went out. This case, we can see that the arc went out very quickly, and this is because of the shunt reactors and because of line is not very long. But I can show you the case of the 330 kilovolt line, single phase short circuit and reclosing. So here we also have minus zero current, and I need to calculate first making the base. So here folded face A, and let's see what we see. So you can see that only here arc is went out. So this period of time was around 83 milliseconds, and if we look on our case with 750 kilovolt line, the arc went out just through the 32 milliseconds. And we also have one more way to determine a period of time when arc is went out. This is can be done through the zero sequence current of the shunt reactor. So during this single phase strip, this zero sequence current has DC component. And when this DC component is went out, so we can determine that also arc is went out. So let's just filter this zero sequence current and look at DC components. So we have filtering. We need a low pass filter. Let's select zero sequence current 30, and here let's make 10. Okay, so we can see that DC component removed like here, and as I understand the process, that means that arc not just only went out, but the air in place of the short circuit is also deionized. So, and this time is also very correlated with experiments and timings that are usually used in IR. So I believe I say all. No, I want to add, show one more case when it's very obvious that arc went out. This like okay, this is the case. So this is the case of the short circuit on the phase C of the 750 kilovolt line, and when we can see such oscillations, is that is a good sign that phase is healthy, because it in the highest amount it's almost like nominal voltage, so like 330 kilovolt. And if talk about this case, we can see that arc is went out is around something. So let's look. Almost here, but here it starts again, and these spikes shows us that. But then it went out, and this case is successful IR. So let's dive a little bit deeper in distance protections. And I want to show and remind you that in Soviet philosophy, all protections that trip single phase act through this 2004 relay panel that has phase selectors, and these phase selectors looks like distance characteristics of these phase selectors looks like that. The impedance is calculated with classical equations for single phase with compensating factor. So let's see this phase selector works correctly. So switch to, we need to add two zones. Sorry, let me take settings. Okay. So this zone is moved to the first quadrant. And this one is moved. Let's add impedance calculator and switch to the phase ground loop. Grounding factor is just real number, and it's about 0.5. So now we need to link signals to line EA, AB, EC, and where are calculated zero sequence current. So this is before they went. So during event we can see that it worked correctly, and phase B is in the zone, and during this pause we can see that only here it also impedance also came into the characteristic. One of the features of this protection panel is that during this R cycle it goes to the it switches to the its own action. So if in this case this 2004 panel also trips. Sorry, maybe just I'm saying a little bit messy. So what I want to add, that during a single phase cycle, these phase selectors are switched to its own trip, and if there will be short circuit on the healthy phases, these phase selectors makes 3-phase trips. So I forget to add about what protections are blocked during single phase R during this pause, because if we look at zero sequence current, line zero sequence current, we can see that it has some amount and it depends on the power that transmitted during the line, and usually the second or third stage of the zero sequence neutral overcurrent protection is blocked during the single phase R, and in this particular case blocked second stage of these protections and also the third stage, but that part of it that worked with teleprotection scheme. We don't need to block any protection that has timings. Time settings that are bigger than the IR cycle from the both ends, because from substation A side in this case we have 1 second pause, but from the substation B side this pause is bigger and it's like 1 second and a half. So let's check that we don't need to block multi-phase distance protection. I want to show one more time that it looks like that, and calculates impedance just by classical equation. In RelayHelper app we have I don't have this particular protection, but we have so let's remove this one. We have Ukrainian protection that can be set by points, and the first stage I insert approximately because it's difficult to make this one half of the circle. So it will be like just we will remember that we have here like half of the circle. So let's insert second zone. I will change color, and third zone, it's enormous because it reserved short circuit on the low side of the auto transformers on the opposite ends. Sorry. Okay, let's I believe I don't even need to relink channels to the calculator, so we have voltages linked, currents linked, so okay. So let's see what happened during short circuit. So it's only in the third zone, this short circuit, and third zone has a lot of time. It has almost 5 seconds, and this so long time, as I said earlier, because it reserved short circuit on the low side of the auto transformers. And during single phase IR, it's just not in the zone. So as I said earlier, in IR cycle we need to block just protections that can trip during this period of time, and if protection has time settings bigger than the this pause, we can just we can not block it. So I believe that with this case we're almost done, and for me it's very exciting to look at these cases, because you know they are very rare, and one short circuit can be in like 3 or 4 years, and it's very interesting to see how this processes during this single or three-phase trips, and for me it's very interesting. But I planned to talk about modern designs and modern protection. So this is like example of the one of the modern design, and usually the modern design, if to look to the primary scheme, usually has this neutral reactor, and in this particular case it has Buchholz relay, differential protection, The shunt reactor has two protections based on RET670. But the functions is like this one old Soviet philosophy, but this philosophy just copied and a little bit developed, but the principles are pretty much the same. So on the shunt reactor we have in this case two differential protections, two IEDs. Each IED has two differential protections. Also this bushing insulation control is implemented in Siemens Relay 7 SJ 86. The auto-stop protection is based on REL 670. The main protection is RED 670, but it utilizes optic channel. There are also two backup protections. And they are usually from different manufacturers, and in this particular case we have REL 670 and 7SA 87, and this backup protection also uses like high frequency communications channels. Each circuit breaker has two breaker control units. And the main difference between old Soviet design and modern design is that this protection that make the main single phase R is not have don't have its own phase selectors. So in the main difference between modern and old designs is that now each protection has its own phase selections logic, and every protection just make single or three phase trips by itself or through the REC 670. Also, this over voltage protection can be done on any modern unit, but in this particular case it implemented in Ukrainian IED. So I believe I say the main differences. And let's look on a little bit on logic of REL 670 because it's more like it's more obvious and easy to see the logic. So this is part of the logic of the neutral overcurrent protection, and this is a binary input that asserted while a single phase IR is in progress. And as we can see in this case, first, second and third stages are blocked. If we look to the distance protection, it blocks only in case of voltage circuits failure. This is like communication logic, and for neutral overcurrent protection we also see these binary inputs that blocked this scheme, but for distance protection it's not blocked. And here we can see the tripping logic, and in these signals we have united signals from all protection functions that has its own phase selection tool. But some of the protections that need to trip single phase don't have this phase selection logic, like for example first stage of the neutral over current protection, like distance, like teleprotection logic, and these protections are connected to this input of the tripping logic, and this input uses this phase selection signals from the phase selection logic of the distance protection, and it generate trip signals of the faulted phase. So here this the logic from the two breakers, and this like very complex, let's say, logic. It's about related to the adaptive single phase R. So the main thing in that logic is that over voltage protection block that active just during I believe you remember this binary input. So this over voltage protection is active only during single phase IR cycle. Here we have signals about which phase is open. I believe all of that can be done much easier, but anyway, it is what it is. These signals are used for tripping phase. So what's the point with this adaptive R? So it measures voltage on the tripped phase. And I said that when voltage started to increase, that means that our arc is went out, and we can switch, we can close the faulted phase. And for instance, the setting of this block can be 60 or 80 kilovolt, and in this case 60 kilovolt we already have here, so we can reduce this pause by using this logic. And if we if we see this case, we can close the faulted phase already here. So already just in that period of time. So after like around 30 milliseconds. So this logic has the minimal time because the problem is, as I said, that air in the place of the fault needs to be deionized. So there are like minimal time. It has to be at least 300 milliseconds. So I believe that I said all that I want to say. Let me check if there are any questions. Okay, I don't see any. There are not a lot of people. But anyway, thank you for watching. See you next time. Peace for everyone.